Okay, welcome back to our discussion of the insertion into B+Trees. Now that we have a grip on the insertion in terms of a few examples that we've studied and a sketch of how insertion is going to happen, let's dive a bit deeper and have a look at pseudocode that would describe how B+Tree insertion is being performed. What we'll see is that this code immediately reflects the recursive nature of the insertion, the bottom-up traversal that or splitting that might happen during insertion. You will immediately see that in the pseudocode and the algorithms that are behind this. I think this is quite elegant setup. All right, so at least for insertion, let's look at the algorithm in more detail. We won't do that for deletion, but actually it's reflected in a sense, so there is some symmetry there. Let's look at insertion for now. The core of that routine would be the tree insert routine. Okay, so the core would be this function that gets two parameters, namely the entry that we need to insert into the B+Tree. Recall that this is, of course, a pair of key value and the associated rid, the row that carries that key value k, okay, and we will try to insert this particular entry into nodes. So this will be one node of the B+Tree. It could be the root node, it could be inner node, it could be a leaf node, depending on what kind of node we have in our hands. This tree insert routine will react accordingly. Okay. Before we look at the code here, let's think about what this routine will return. Okay, so this is a function that has a return value, and the code is organized such that if this function returns a pair of this form, let me draw this. Okay, so this function returns a pair. If this is a pair of this form in which the two entries of the pair are set to undefined or nil or bottom or whatever your programming language gives you at this particular point. So if this is the return value of the tree insert routine, then this is an indicator that no further recursive upwards splitting has to be performed. So no further splitting has to be performed. All right, so this is how a tree insert communicates to its caller that the insertion is already been done, no upward splitting is needed. The other possible return value is this. It's a separator value and a page pointer that's associated with that. Let me draw it like this. So of course it's a pair again. In this case, not bottom or nil, but with a well-defined separator key value and the pointer to an index node that that is associated with the separator value. This is an indication that a recursive insertion has to happen. So we need the insertion of this particular separator value and its pointer into an inner node of the tree. Okay, so these are the two possible return values. Let's remember that. Okay, so now let's look at the insertion routine itself. It will, of course, first inspect the node that we have at hand here. Okay, if this node is already a leaf node, then no further recursive descent into the tree is necessary. And we can call a particular routine, an auxiliary routine, that will know how to insert one new index entry into a leaf node. Okay, that's the leaf insert routine. Okay. All right, so node appears to not be a leaf node. It has to be an inner node. So we have to perform search. We have to descend further into the tree until we hit the particular leaf node in the leaf level that should hold this new index entry k, rid. Okay, so we will just perform the regular tree search that we already discussed when we looked at tree search. Okay, so well, we will look at the key value of the index entry. That key value will tell us into which of the subtrees we have to descend. Okay, so if the key value k is even smaller than the k1 value in this inner node, then we have to perform descent into the leftmost tree pointer, which is the p0 pointer. Okay, so we try to insert the k, rid, the new index entry, into the subtree pointed to by p0. Otherwise, we will use binary search to find the correct insertion point, the correct pointer to follow, the correct page pointer to descend into, and then we'll call ourselves recursively to perform the insertion in this particular subtree. At one point, we will hit a leaf node, and we will end the recursion by calling leaf insert here at this point. Okay, so this is tree insert, and as such we know what the return value of tree insert is. It's a pair of a separator and a page pointer. So this is what we capture here. Once tree insert returns, we capture this return separator and page pointer, so just so we know that, or just so we can inspect and decide whether further upwards splitting and insertion has to happen, yes or no. Okay, so once we've performed these recursive calls and they've returned, we inspect the return value and check whether it's separator, whether the left part of the pair is indeed this bottom or nil value. If this is the case, then no further upwards insertion has to happen. All right, so our job is done, and this is what we return and indicate to our caller. If the insertion process below, in the subtrees below, have already been performed completely and no further upwards insertion is needed, then this is the same good news that we report to our callers, so to the upward tree levels. All right, so this implements that once we find a node that really can accommodate the new index entry without any splitting, without any upwards propagation of new separator pointer pairs, once we detect that, it stays that way and we do not propagate insertion further upwards. Okay. Well, if there is indeed further upwards insertion to be performed because the separator pointer pair is not nil, then the next task we have to perform. We have to insert this separator pointer pair into the current node. Okay, and we know that this will be an inner insert, otherwise we would have hit the leaf insert case. Okay, so in this case, indeed some insertion of this new separator pointer pair into the node has to happen. Of course, as you can easily see, inner insert and leaf insert are the return or define the return values of this tree insert routine. So we expect leaf insert and inner insert to also return a pair of this particular shape. And we will see this in a second when we look at leaf insert and inner insert. So this is the tree descent logic, and weaved into that is also the upwards propagation of inserts that might be needed if we have split on the lower levels. So this is the backbone of the whole thing, the tree insert routine. Let's now look at leaf insert. Okay. So leaf insert, we are aware that node is indeed a leaf node, and we are tasked with placing this particular entry inside this leaf node. Okay, so let's check whether there is still space in the leaf node, and that would be the check that we have to perform. Are we already at maximum occupancy? If this is not the case, well, then it's fine. We can just place the new index entry in this particular leaf node. Of course, this insert means that we do a sorted insertion between the other index entries inside that leaf node. Okay, so stuff has been placed there. Maybe the leaf is now at maximum occupancy, but we don't care. This k,rid new entry has found its place into in the leaf node, and we are done. We indicate this by returning this particular value, indicating to our caller that no further splits have to happen. All right. In the other case, and that's this case, indeed a leaf split has to happen. Okay, so let's allocate P' a new leaf page. Let's first collect all the entries that we now need to distribute among these pages node, the original leaf, and P', which would be the new leaf. We've got 2 O plus 1 entries. So 2 O entries on the old leaf node plus one more entry, the entry that we have to insert actually. So we have a collection of 2 O plus 1 such index entries that need to be placed in the old node and in the new node P'. And that's what we do. We split We split the load between the node and place O entries here, and place O plus 1 entries, O plus 1 entries are being placed here. Okay, so the load is almost evenly split between node and P prime. Okay, and now recall that we are splitting on the leaf level. Splitting on the leaf level means we copy the new separator upwards to our callers. All right, so the new separator is indeed this. Well, actually, the separator is only this value. All right, it's the key value. It's the minimum key value on the new page P prime. So this is the new separator along with its pointer, of course, to P prime. That has to be inserted in the level above us. This is what we report to our caller, and it will trigger our caller to perform the insertion of this new separator pointer pair into the correct inner nodes. Okay, so copy up. KO plus 1 remains here and is also copied upwards as a new separator as a return value here. So that would be the leaf insert. Now to the inner insert. Okay, the inner insert would be tasked with placing a new separator pointer pair into this inner node. Okay, all right, so let's see whether that inner node can accommodate this new separator pointer pair. If that inner node has not reached maximum occupancy, well, then just let's place separator pointer pair into this inner node and everything is done. Okay, so that directory reflects the leaf insert case and we report as much so that no further upwards insertion are being performed. Perfect. Otherwise, that inner node has been overflowing. Okay, so we allocate P prime, which would be a new inner node page. Again, we would collect all the entries that are now to be distributed between the old node and the new inner node P prime. And this would be the entries. Note that there is this extra entry, this P0 entry, which has already been part of the inner node and we won't forget about it. All right. So, well, this is the load that we have to distribute between node and P prime. And again, we will do this split evenly. We will place O entries here. We will place O entries here. Okay. We will move up. We will move up the KO plus 1 key value. Okay. The new separator between the node and the P prime page. We will only leave its PO plus 1 pointer down here in the P prime page. Look how nicely this works. We copy up the separator and it's being moved upwards the tree, but its page pointer is left here as the new P0 pointer on the new P prime allocated inner node page. I think this is a beautiful arrangement in this algorithm at this particular point. All right, so both inner nodes have this characteristic P0 pointer, which is used to point to the leftmost subtree in which the smallest entries are being found. All right, because this has left this pointer on its own, well, we just use its separator value and copy it upwards the tree together with the page pointer that will point to the newly allocated inner node. All right. So yeah, that's the inner insert. A very simple thing to do. I think we are almost done. So we've got tree insert, we got a leaf insert, we got inner insert. We only need one routine to trigger the whole thing to as an entry point, as an API entry point into the insertion of B+Trees. And that would be provided by the insert routine. This would be the top level routine, the top level API that we would expose to the rest of the database system. In this top level API, we would simply request that this new index entry has to be placed inside our B+Tree. Okay, so let's see what's happened there. This is a rather short routine. Okay, so well, we would just use tree insert, which would start the recursive descent and start the search for the correct leaf node to insert our new entry. Of course, this recursive descent will start at the root node, so behind this variable root, this special variable, you'll find the root of this B+Tree that we would like to insert into. Okay, so tree insert will do its job. It will perform all the splitting and all the maintenance of the leaf and inner nodes, and it will report back. It will report back with this pair, if you recall, and this pair indicates whether a split has to happen, a further split has to happen at this level, or if everything is done already. Okay, so if indeed this K prime, or even if the entire pair is filled with nil or undefined values, or bottom values, if you will, then everything is done already. So everything is done already. The rest of the tree could accommodate this new index entry, and nothing has to be done. If this entry is not nil, then this is the very rare case that we indeed have to allocate a new root node. We have to allocate a new root node because the root node here has been split. All right. The new separator that is to be used has actually been reported. That's K prime. It actually came back. So let's allocate a new root page. This is the allocation of the new root page. Let me highlight that. This is the allocation of the new root page. Okay, so this is the new allocation. All right. It will be the new root after we have performed our job. So this static variable, if you will hold the new root pointer. At this point in time, all the path length in the tree have been increased by 1. Inside the new root node, we will place a pointer to the old root node, and we place a new index entry here, a new index entry using separator K prime and the pointer to the newly allocated root, node that was created when we split the old root node. So this would be the setup now. This would be the new root of our B+Tree. It has a single entry here, a single index entry K prime. Its P0 pointer would point to the old root. Its this index entry pointer would point to the sibling of the old root. These have been This page has been derived from splitting this old root node. So this is the new setup. All right. The B-tree height has increased by 1. And that completes the whole routine. All right. What we see here, what we very clearly see is that this root node, the newly created root node, holds a single index entry, 2 pointers and just a single separator here. It clearly violates the minimum occupancy rule, and it's the only node, inside our B+Tree that is allowed to do so. If you recall our live descent into the B+Tree a few videos back, then if you switch back to this video, you will see that there was a root node in the B+Tree that we inspected. I think that only carried like 10 index entries, which is way below the minimum occupancy, way below the order of the B+Tree. This has been a sign that even in PostgreSQL, this minimum occupancy rule of the root node can be violated. Okay. So that completes our discussion of the insertion code. There's one more thing I would like to mention regarding B+Tree insertion, and it's a technique or a trick that we can sometimes use to postpone splitting, to postpone the splitting of nodes, which can lead to more splitting in the upper levels and may even lead to B-tree height growth. So if we can postpone that, that would be a net win, I would say. So, and that technique is very simple. It's the redistribution during B+Tree insertion. It can help to improve the average occupancy and may delay splits and thus may delay height increase in these B+Trees. Okay, and this redistribution is actually very nicely supported by the chaining of the nodes in the same level, B+Tree level. Recall that the sequence set nodes are chained among each other, so that would be the chain I'm just talking about, the chain pointers. And even and even the inner index node levels in B+ in PostgreSQL are chained together using such bidirectional pointers here. These come in handy now, as you will see in a minute. Okay, so let's see how the redistribution of node load can work in such a case. Let's assume that this is the B+Tree. It's a very small B+Tree that we are currently looking at, and it has to accommodate a new entry, 6, rid. Okay, we have to insert that. The insertion routine will lead us with a recursive tree search into this leftmost leaf here, which cannot accommodate a new node. Okay, but its rightmost sibling, which is this node, it has space. There is indeed space, and we could place a new entry there. 6 only has to go in this particular node, so we have to do a little bit of reorganization and a very local reorganization to fix the situation and to accommodate the new entry without splitting any nodes and risking the B+Tree height growth. Okay, and well, the technique is very simple. Well, we would just use one entry of this overflowing leaf node, and we'll push it over to its right sibling, which has some space to spare. All right. This means that one entry from this leaf node wanders over to this entry, and this means, and this is extra highlighted here because one could forget about this, we may have to update the separator value in the parent node of these two sibling leaf nodes. Okay. So just push over one entry into the right sibling here, but don't forget to update the separator value that might have changed so that later searches will correctly descend into the left or right leaf here. Okay, so let's see how this has to work if we enter this new entry 6 and use redistribution. That's shown on the next slide. Okay. So adding the 6 into the mix would leave us in the left node with entries 2, 3, 5, 6, 7. That's one entry too much. One of these entries, the largest entry, will be pushed over to the right sibling, and we can easily locate and find the right sibling and inspect its contents using these sequence set chain pointers. Okay. So 2, 3, 5, 6, 7 have to be placed here. So we will leave the smaller entries in the original leaf node, and one entry, the 7, has been pushed over here. Okay. Now recall that the old separator entry in the parent of these two nodes has been 13. It has to be 7 now, otherwise we would not be able to locate the newly pushed over 7 on future searches. All right, so the new smallest leftmost value here after redistribution has to find its way up as the new separator in this inner node here. But that's about it. There's new entry to be placed here in the inner node. We just replaced the 13 by 7. This does not alter the occupancy of the inner node. It has been full already, but it's not fuller now. Everything is fine, so we could postpone a split of this leaf node and thus postpone a split of this inner node. And who knows how far this split would have been traveled up, maybe even up to the root. All right, so much for B+Tree insertion and the algorithm behind that and this tiny trick that is called redistribution. You find redistribution indeed implemented in B+Tree implementations. Some of the techniques that we are discussing here, especially when it comes to deletion, are not actually implemented inside B+Tree implementations out there, because well, the savings or the benefits that you get from these more complicated B+Tree maintenance routines tend to diminish with the complexity of these algorithms. So sometimes simplicity beats complexity, even if you could theoretically postpone more splits in the B+Tree and so on. So some techniques that we discuss here are not actually found in B+Tree implementations, but they are still part of the original B+Tree algorithm proposal by Rudy Beyer and Ed McCreight. Okay, so much for B+Tree insertion. Let's draw a line here. Next video, B+Tree deletion. I hope to see you then. Bye-bye.